Alright, this video has to do with electrochemistry, and we're going to look at the electrolysis cells as well as some of the important equations for the spontaneous cells, such as looking at the relationship between delta G, K, and E cell. And so this is electrochemistry part 2 video. Alright, so we start then with the relationship between delta G and E cell in red here. So this is an equation that's given to you, and N is going to be the number of moles of electrons that transfer through the wire. F will be Faraday's constant, and E cell can be calculated from the tables. So put that all together and you have delta G, or work. I think on the last video we said that work is the maximum work that can be obtained from the system is equal to delta G. So, let's see, one mistake I see already. You want to have a little 0 there to indicate for the standard value for delta G. Alright, so then in this example we're going to calculate delta G in E cell for the following reaction, and the reaction is given that the concentrations here are 1 molar. 1 molar is the standard state for solution concentrations. Alright, so it's given to you as the electrochemical notation. Remember, you have on the left hand side you have the loss of electrons, so that's the oxidation. On the right hand side, electrons are gained, that's reduction. And remember, it's going to be reduction minus oxidation when you're calculating values of E cell. And on the next line here, I broke it up into the half reactions. Notice that I have 2's here, and that's because you have a 2 for the zinc, and if you need to have the number of electrons gained and equal to the number of electrons lost. This is the value for 1 silver plus 1 electron forms 1 silver solid, and you do not multiply the voltages by 2 just because you put the coefficients over there. All right, so then you need to think about the sense of this for the reacts. This information would be as written in their standard reduction tables, where the electrons for both half reactions are written on the left-hand side. So which one do we have to flip? You can notice that you have the larger one on top and the smaller one on the bottom. For the spontaneous reaction, it's going to be larger minus smaller. The other way you can think about it here is the silver is the reduction, so that one's going to go as written, and the zinc is the oxidation, so you're looking at zinc going to zinc 2, so this one has to be flipped, and that's consistent with the fact that you have to subtract this one. Alright, so then you could rewrite this as 2 silver plus, let me leave off the phases here, plus 2 electrons forms 2 silver solid, and that's going to be E0 is equal to 0.80, and then flip the second one, so this is going to be zinc solid forming zinc 2 plus aqueous plus 2 electrons. So you're going to take the negative of what's in the table, and then you're going to add them together to get 1.56 volts. Okay, then you can use this. This is E0 cell. You can use this in the equation on red there to calculate delta G. All right, and we are going to use delta G standard is negative NFE cell, and delta G then will be equal to, you have 1 mole, it's a 1 molar solution, so you have 1 mole in 1 liter, and that's going to be a mole of zinc, okay, and then there are 2 moles of electrons for every 1 mole of zinc. Then, so this combined is N, the number of electrons that pass through the wire. Then F, Faraday's constant, 9.65 times 10 to the 4th. coulombs per mole of electrons. Then you have, E cell, which is 1.56. This is the standard voltage. So moles are going to cancel. We're going to have coulomb times volt, and remember coulomb times volt is a joule. So delta G has the right units, and this is going to be equal to, and I forgot to put in the negative sign here. Okay, so this is negative 3.01 times 10 to the 5th joules, which is equal to negative 301 kilojoules. So you can think about that either way. So that's delta G for the reaction, and we've gotten it from E cell. So that's a pretty important connection there. Now on this slide, you can, we want to know what the relationship between we just looked at E cell and delta G. Now we want to know what E cell is to K. What's that relationship? So that one you can start with delta G is equal to negative RT natural log of K, and delta G is NF E cell. Put them together, solve for E cell, and that's going to be equal to RT log K divided by NF. All right, now if you want to put this in base 10 log, E cell will be 2.303 RT base 10 logarithm of K divided by NF. Now the next step is to take all of these constants right there. So what is this? You have 2.303 times 8.314 joules per mole Kelvin, 25 degrees C, so this is 298 for the standard temperature. Faraday's constant, 9.6510 to the 4th coulombs per mole of electrons. Put that all together, and you have a new number. Let me move it over a little bit. So E cell equals 0.0592 divided by N times the base 10 logarithm of K. So this is a very important relationship there. And that's the relationship between E cell and K. Now, if you look at the little diagram on the lower right, this is a summary of the relationships. And if you want to know the relationship between delta G and E cell, so delta G and E cell, it's NF E cell. If you want to know the relationship between delta G and K, it's going to be negative RT log K. Delta G is negative RT log K. This is the equation that I just derived, the relationship between E cell and K. The form that I just gave you, is right here. So this equation is the one in the box right there. Base 10 logarithm of K. All right, so if you think about it in terms of this little triangle, that can help quite a bit going back and forth and around and around. All right, next thing here is to actually use the equation that we just derived, and it's 0.0592 times the logarithm of K divided by N. And we'll do it for the reaction that we've been looking at here between silver and zinc, and the voltage that we calculated 2 slides ago was 1.56 volts. So if you want the standard K, you're going to use your E cell that you calculate from the tables. And in the case of our reaction, remember it was 2 silver plus 2 electrons, so N is going to be equal to 2 here. And then solve for it. In this case, there are no gases, so we're going to say K is equal to Kc. And look how large it is. So it's very large, and that means that it's a spontaneous reaction. The fact that you've got a positive E cell also tells you it's a spontaneous reaction. And delta G for that reaction, if you recall, was equal to negative 301 kilojoules. So that's a very big number. So all indicators here are that the reaction is spontaneous. Again, you got a positive E cell, a large value of K, and a large negative value of delta G. So the reaction is spontaneous. All right, now the Nernst equation is derived here. This is a very important one to know. And this equation on the top here was derived earlier in the chapter on thermodynamics. So when the system is not at equilibrium, you have Q instead of K, and then you have a delta G excuse me, associated with it not being at equilibrium. So we can substitute in delta G is negative NFE here. This is non-standard. Oh, I know I was going to say that. When we say the system's not at equilibrium, in the case of electrochemistry, usually we're talking about the fact that the concentrations are not the standard concentration of 1 molar. So that's why we say, well, you know, the Nernst equation gives you information about concentrations other than 1 molar. So it's not that the system's on the way to equilibrium in the sense that we talked about it in thermodynamics, but instead it's not, these concentrations in this ratio are not 1 molar. Okay. Anyway, so that means you're going to get a non-standard value of delta G if it's not 1 molar, concentration is not 1 molar. So you get a non-standard equation for using E non-standard on the left, and so it'll be delta G standard minus NFE cell standard. And then you can solve for E cell. This actually should have the word cell right there. So it's E cell, but you don't have the little 0 on the top telling you that it's standard. So that's, then you solve for E cell, and it's equal to E standard cell minus 2.303 RT base 10 logarithm of Q after you make the substitution between natural log and base 10 log. Go ahead and solve for that. Clean it up a little bit, and that means that we're doing the same thing again. We take 2.303 RT right here. And it looks like something's missing here, the F for Faraday's constant. All right, so then you take 2.303 times R times T, and then it's divided by F, and that's what you use. That turns out to be 0.0592. And it's similar to the last equation that we derived for E standard cell being 0.0592 log K over N. But it's different because you're not solving for E cell standard. You're starting for E cell when the concentrations are not 1. So that's the real importance, the value, the significance of the Nernst equation. You can calculate the E cell standard, but then you have to use it in the Nernst equation to calculate the non-standard value. Our Nernst equation, and whoops. All right, so for this example, this is zinc and copper. Notice that the concentration of zinc 2 plus is 1.0 times 10 to the minus 5 molar. The M is missing here. And the copper is 1 molar. So this is a non-standard cell. And it's written in terms of the electrochemical notation here. You can rewrite it if you please to, if you want to, in order to kind of get a better sense of it if it's just written as the regular balanced equation. And then you're going to look for the numbers in the table. Copper is going to be the one that's picking up the electrons. It's easier to see in this form than it is in this form, that copper is picking up the electrons and becoming reduced. So if you look in your electrochemical table, you're going to find copper 2 plus 2 electrons is equal to 0.34. Then you got the loss of electrons by zinc, so that's oxidation. You're going to find negative 0.76 for the reduction of zinc 2 plus 2 electrons forming zinc. So you have to flip it to get the oxidation. So you're taking, you're adding the negative of negative 0.76. You can follow that. You get 1.10 for that reaction for E cell standard. Then you want to use the Nernst equation. In this case, we're going to calculate, let's see, the value of E cell, given all the information so far. All right, so on the next blank slide here, we will, I'm going to have to write this over again rather than going back and forth. So if you have zinc solid plus copper 2 plus forming zinc 2 plus copper solid, then you're going to write the expression for Q as the concentration of zinc 2 plus times copper solid, and then divide that by the concentration of zinc solid, you know where I'm going with this, and divided by copper 2 plus aqueous. So copper solid goes to 1 by definition, zinc solid goes to 1 by definition, and then you have Q is equal to zinc 2 plus concentration divided by copper 2 plus concentration. So this is going to be equal to, the zinc is 1.0 times 10 to the minus 5 molar, and the copper is, I think I said 1 molar before, it's 0.10. Better check that. Yeah, that's a typo in the problem. It's supposed to be 0.10 molar. I have to go back and get that. Okay, so then this will be Q equal to 1.00 times 10 to the minus 4. And the units are both molar, so they're going to cancel. And that will be the value of Q. Then you go and put it into the Nernst equation. E cell non-standard is E cell standard minus 0.0592 over n, which is 2, times the logarithm of Q, which is 1, times 10 to the minus 4. And you have that 1.10 volts minus a negative 0.12. So you get 1.22 volts. So if you think about it, if you've done this experiment in the lab where you're working with solutions that are not exactly 1 molar, oftentimes you'll get a voltage using your voltmeter that's not exactly equal to the standard value. It's off by a little bit, and that's because your concentrations are not exactly 1 molar. All right, then. Okay, so for this slide, this is looking at the relationship between the pH of your solution and the voltage. So it has to be an electrochemical cell. And we can use the zinc hydrogen system as our example. And we can look at the measurement of E cell, first of all, of this system, and notice that it is not standard because concentration is not, for the test solution right here, is not 1 molar. Therefore, we're not interested in the standard cell, where we want the measured cell, which depends on the concentration. All right, so if we write this out in terms of the reaction notation rather than this electrochemical notation here, then it's easier. And since we're going to use the Nernst equation, we need Q. So work with this form. Okay, so Q will be equal to the zinc 2 plus, which is 1 molar, divided by partial pressure of hydrogen, which is 1 atmosphere, divided by the unknown concentration of H plus squared, and then zinc would not be in the equation because it's equal to 1. Also, the pressure is 1 atmosphere, which is the standard state, so that's going to go away. And since zinc 2 plus is 1, you'll end up with 1 divided by H plus squared for Q. Plug it into the NernStandard equation. And let me blow this up. I wanted to write out a little bit. Okay, NernStandard equation, you have your standard 0.76 volts minus 0.0592 over 2 electrons for this system times the logarithm of Q, which is 1 over H plus squared. Now, I didn't write it down here, but I can add one more line to clarify a little bit. E cell is equal to 0.76 volts minus 0.0592 over 2, and you can write it as logarithm of H plus to the negative 2, right? Then, in the next line, you can take this negative 2, bring it out of the logarithm expression, it becomes multiplicative. So you have negative 2 times negative 1/2, so that's going to be positive 1, times 0.0592 base 10 logarithm of H plus. Okay, all fine, except that you want to go from here to here, and you want to use negative log H plus is equal to the pH. So that means you want to multiply this term times negative 1, therefore it'll make this term negative. Then in the next line it's negative times negative log H plus to give you this, and then that's equal to pH. You can plug it in right there. All right, now solve for pH, and you've got 0.76 minus the measured cell potential divided by 0.0592, and it's very interesting to see here that the pH for an electrochemical reaction where one of the half reactions is hydrogen, okay, is some version of the voltage. So in other words, a pH meter is a voltmeter where the hydrogen cell is used as one of the half reactions. It's a pretty remarkable thing here. Never knew that. But that's the connection between those two. Now, if you're not using zinc as your counter ion, then you're not going to have 0.76. If you had copper, you'd have negative 0.34 here, just as an example. So when you look for this equation in your book, it'll be some version of this, but not necessarily 0.76. If it's a negative value, then the negative comes out here, and then it's positive. And so there's different variations on it, but anyway, you get the very nice relationship between pH and E cell. On the next slide is a different topic. This is concentration cell, and I think you might have worked with this one in the lab. So let me start by drawing the cell, and I'm going to move this over here. See if I can put all this together. So this system has two solutions of copper 2 plus. So maybe it's copper sulfate. And on the left-hand side, it's 0.050 molar. On the right-hand side, it's 0.50 molar. So the concentrated is on the right and the dilute is on the left. Okay, then they're in equilibrium with these copper strips. Those are the same. The wire to the voltmeter, over like that, and over to the right-hand side, and then you've got this balance of charge associated with the salt bridge, but we won't worry about that. We know what's going on there. Okay. All right, now the thermodynamic tendency is for the electrons to flow so that some of the copper 2 becomes copper solid, and that it reduces the concentration of the copper 2. So in other words, if the electrons are moving in this direction, they're going to end up on the electrode. The copper 2 plus that's in solution wants them, will grab them, and form copper solid. So this is the right-hand side, you're going to see a buildup of copper solid, on the electrode. But there's the main point here is that there's a reduction in the amount of copper. All right, now on the other side, what happened? How did the electrons end up moving? So on the left-hand side, the copper solid became copper 2 plus. So this was copper solid here. So you got copper solid becoming copper 2 plus 2 electrons. On the right hand side, you've got copper 2 plus 2 electrons forming copper solid. All right. So the tendency is, because the concentrations of these solutions are different, the tendency is for the electrons to flow until the concentrations of copper 2 plus on the left equals the concentration of copper 2 plus on the right. So the copper 2 plus here, that is the solution, is increasing. So copper 2 plus is increasing on this side, so it's becoming more concentrated. But copper 2 plus is decreasing on this side, so this is becoming less concentrated. So in time, this will go up to some certain concentration, and in time, this will go down to that exact same concentration. The electrons will stop flowing when the two copper concentrations are the same. That's the basis of the copper concentration cell. So then, if that's the situation, then you have copper becoming copper 2 plus on this line, copper 2 plus becoming copper solid on this one. So the sum of the two voltages is going to be 0. And the net result here is that this is the overall reaction. If you're going to write the expression for Q, it's going to be the dilute divided by the concentrated. That's the way it works out for Q. For these types of reactions. N equals 2, E cell is 0, E standard cell is 0, and then go ahead and do that, and you end up with 0.03 volts for the system. And this changes depending on the concentrations of these to start with. So as the cell operates, the concentration of copper 2 plus in the diluted cell increases, and the concentration of copper 2 plus in the concentrated cell decreases. And there's a voltage associated with that. So I'm going to stop here. I do have a couple more slides on electrolysis, but I think I'm going to do a part 3 instead because this is just too long. And we got some detailed work to do for the electrolytic cells. So I'll stop here, disregard the rest of the slides. I'll copy those into the new part 3, and I'll pick that up in just a sec.